Good afternoon, everyone. My name is Peter Olendzki, like Ian mentioned. I work with Ian at Intuitive Corporation. We've been around for a couple of years now. The company just started last year, January of last year. Majority of our staff is a walkover. A lot of them are ex-employees of Hakro Yalis. And it was great to hear some of the insight from a mechanical perspective from TNP. We're currently working on a lot of projects with them, and it'll be nice to give a perspective for BIM from a structural standpoint. So let's give a quick overrun of what I'll be speaking about. In my intro, in the time I've spent in the past 2 or 3 years using BIM, I first started using the Autodesk products that were out there. I used Revit for about a year. And then after I had some time to try out some new software, I found that there are certain parts of different softwares that offer more advantages from a structural perspective. And I also found that the process itself is starting to change. I'll go through that and sort of how BIM and 3D modeling can or has changed, and how the roles of people who use Autodesk products in the past, how they've changed now, and some examples how I've seen that at our office. The first case study, which will be about 80% of the slides that I have, it'll be the RIPLEY'S Aquarium of Canada, which TNP touched upon there. And some of the lessons that we learned there and how we applied it to our next project, and a lot of it overlaps with the segment 2. So I'll just it'll be about 20% of the slides, and I'll touch upon some of the newer lessons that we learned there. So the way that I see BIM and how I think things have changed, this is an IFC export of the Ripley's project that we're working on. Our job as structural engineers is to take that, whether it's from a 3D model or from drawing sheets, and to analyze it, design all the components, and somehow reflect that. So in the past, from what I've seen and when I first came out of school, the process that was typically used was the architects and the consultants. They would start with their hand sketches, and I would move to AutoCAD. And typically, you'd go from plans to sections to elevations, and that would go all the way from schematic phase, and it would move on until the whole thing was built on site. And I think one big mistake that has been made in the past year or two is that a lot of people who are using this approach as in the past, they think that you just keep adding 2D drawings, and the people in the past who use AutoCAD, they just keep putting this information from 2D hand sketches or CAD files, and that produces a 3D file. So I was working with some of the, I don't want to use this word, but some of the older guys at our office, and they would all say, well, yeah, you just keep giving them 2D files, and in the end, you end up with a 3D model. And I think that total approach to BIM from a design perspective, whether you're an architect or a structural engineer, is not right. So what I've tried to use and try to implement in our office is a separate approach here, and it's what I think is, if you make and you think about the design and the actual process from a 3D perspective, and you put your design intent into a 3D environment, then essentially what you're doing is you're creating, you can use, I'll call it snapshots from the model itself. So if you invest the time to properly coordinate and to model and everything, then you'll have everything that you need from the 3D model itself. You don't have to be working the opposite way. And one concrete example that actually came up at our office, this is a flight of stairs that are being used in an art gallery. They're about 8 meters tall, steel stairs. It was a main feature of the structure there. So what happened was we had Ferdo. He's a steel design specialist from our office. He was given the actual work to do these stairs, and again, he likes doing everything old school. So he took what the architect had, and he framed in what he thought the structural steel for the stairs was. Now, when Ina, who was our BIM specialist, got the markups, she sat down and she opened up the model, and now it was on her to somehow know how to transfer this information here into what the architect wanted. Now, this project was a full BIM project, so they wanted all of our steel, all of the framing, in the exact spot, so it couldn't be kind of put in the middle of the stairs or under the stairs. They had to know exactly where it went, and what we found was that from a perspective where someone in the past would just take 2D sketches from someone and put them in CAD, there was a lot of assumptions that she had to make now. So what really should have happened is if Ferdo were to want to translate what he wanted those stairs to be sized like, or what all the edge details were supposed to be, he would actually have to give her plans and then provide some sort of section at almost in every step for the BIM modeler to actually understand what she was supposed to show there. So what ended up happening for this project was we actually had an engineer sit down, and they modeled the whole thing. So as they took various sizes and they started to model in and make it fit with what the architect was showing, any assumptions that came up in terms of how certain steel is shown, it was all resolved at that point. So again, I guess the point I'm trying to make again is that the whole process, it can't be thought in the same way that it was in the past, that you just keep making 2D drawings and you end up with a 3D model. I think that a lot more upfront time should be spent, and that you should invest into getting the model properly made. And then from there, any drawings you need should just naturally be made from the model itself. So the first case study, it's the Ripley's Aquarium of Canada. Just give you some brief stats. So it's getting built at the base of the CN Tower there, right by the Rogers Center. It's a 135,000 square foot facility. It's expected to hold about 1.5 million gallons of water. It's expected to have about 13,000 different types of exotic fish. This is a picture of the architect's Revit BIM model. And this here is just a fly-in. This is the main shark tank, and just a cool movie where they're expected to have a moving walkway, and you can actually move to the shark tank itself. They're gonna have 10 to 12 foot shagger tarks, guitarfish, and various other sea life. And on the right hand side is a list of all the players involved. So the client was Ripley's, B&H were the architects, Intuitive was the structural consultant, TMP, as David had mentioned, were the mechanical consultants. PLC was the contractor. Peller was, we had Special Aquatic Concrete on the project. Benson Steel, which I'll touch upon after. We did some neat stuff with them. And MWH was in charge of doing all the life support. So why was this project perfect for BIM? Well, the natural geometric complex nature of the project itself would have been hard to translate anything that the architect was showing from elevations or sections and try to figure out a structural system for it. There was the coordination aspect. A lot of people sort of made the analogy to this project that it was similar to a water plant. Aside from trying to snake all the structural through the architect's model, we had to snake all the mechanical stuff. And on the bottom right-hand corner, you can see that there was a whole separate system that had to intertwine, and that was all the life support systems for the various water tanks. And throughout the project, again, there were various times where we would overlay models and make sure that everything fit. And from a structural engineering perspective, one of the main benefits for this project was the visualization of creative solutions. So when we first saw the project, various framing options might have not been as obvious until we got the model itself, and it's actually great how many ideas can come up when you just have a 3D model and you spend a few minutes playing around with it. So the sort of BIM process, and I want to give you an outline that I guess Revit's not the only tool out there that you can use for BIM. The whole process of how this project started, B&H did the whole massing in Google SketchUp. They did a lot of interior coordination with RJC architects from down south, and they initially coordinated and did a total sort of, I guess, semi-BIM model, and that was all done with the interior and exterior massing in Google SketchUp. And the purpose of that was so the client could have an actual 3D view of what the exterior and interior concepts were. And then once the client was happy with how everything looked, they had the painstaking task of transferring all that information, so the external 3D massing, all the 3D cladding, all the external stuff, and all the interior information from a CAD file and from a Google SketchUp file into their Revit file. So once the schematic phase was passed and the consultants got on board, B&H actually used their Revit model not to create any of their drawings. They decided to do all that in AutoCAD, and Revit was used as a tool with the consultants to do class checks and to see how the structural and the mechanical parts of the model fit, and develop all their wall sections, details, so on and so forth. Structural, we initially did all of our work for the concrete and for the steel in the Autodesk products. There were a handful of sheets that we used AutoCAD for. And then partway through the project, because of the complexity of the project, we decided to transfer some of this information from Revit to, there's another 3D modeling software primarily used for steel, but it does a lot of concrete modeling as well. And it was the Tekla software. TMP, as David had mentioned, they did all their work in Revit MEP. And Peller, which was working with us, they were a aquatic concrete specialist. They did all of their work, all their sections and plans in AutoCAD, and then we transferred that information to our model. So one of the main challenges that our office faced was we were getting information from all these models. So Revit has its own type of model. When you're using the Tekla software, it has its own model, but there's the concrete was done in one software, and all of the steel was done in a separate software, and the drawings were made in two separate softwares. But one useful aspect between the two softwares was to make sure that from an internal perspective that everything lined up. We would export IFC files from our concrete model, import them into our steel file, and do the same with the steel. So we would export all of that via IFC and coordinate all of our concrete. The one minor downfall that we found from that was in areas where steel either sat on concrete or had to integrate with the concrete itself. We would have to remodel a lot of it. So when we were cutting certain elevations and sections throughout our steel structure, we did lose some time in having to remodel certain things. And with the help of the actual 3D model itself, being able to visualize how the whole thing fits, and the process of how we envision the steel getting put up on site, it actually gave us an idea of how to frame the whole thing. So we visualized, or we tried to visualize the whole structure as two separate parts. So what you saw there was all the primary steel, and then from that it helped us create this concept of hanging frames from the primary structure itself, and it sort of gave a repetitive nature to all the steel. So this is it broken down here. On the top left, you can see that the primary structure was somewhat straightforward. It was just your basic columns and steel roof framing throughout, and then the complex nature of it kind of came on the bottom right. And by using the 3D software, what we could do was within the Tekla software, we could import the architect's Revit file, and that was again done through IFCs. So all of the coordination was done in the 3D space. On the right-hand side, you can see that the cladding itself, all of the steel framing was put in fairly tight, so we knew everything would fit fairly well. And on the left-hand side, you can see the primary framing and all of our sort of red frame concepts throughout. And we tried to make sure everything fit well. Another aspect another issue that came up was the architects would be sending us wall sections that they had cut, and they'd be telling us that there's beams penetrating through our own beams, which we had a hard time with. We knew that wasn't a problem. So when we would ask them, where this section come from, they would send us this. And basically, it'd be an area where there's a lot of steel that's coming in from separate angles. And what they would do is just cut the face at that point, like it was a 2D wall section. And they would think that we had coordination problems. And when you actually look at the model, that's an actual section that they cut there. So it made us realize that it was important from a consultant's perspective. If you're working in a 3D environment, you have to make sure that you're visualizing in a 3D environment. And it gave us the problem of how are we supposed to show this if we're not going to be bidding out our model, but the actual the actual sheets, all of our plans and elevations and that kind of stuff. How do we use those drawings to accurately show what we had here? So that was kind of the irony that we found in the whole thing. Usually it's the opposite way. You're looking at CAD files, and you might miss half the steel because you're not really sure what the intent is. Whereas here we were fairly confident that we had all the steel and all the framing that we needed to have. However, we weren't sure what the most optimal or what the optimal way to show this in our sheets was. So we tried a few ways. First, we just tried cutting sections directly from the model. You can see that on the left. And it was our office's first time using the software and ended up being one of the more complex ones. So it's safe to say that the sections and details weren't that clean. So our next step was we tried to export all of these sections and details to AutoCAD to clean them up. And that worked well the first time around. But then anytime any piece of steel moved or any section changed, we would have to re-export the model itself and re-clean the whole thing, and we found it was taking way too long. So what we ended up actually doing, and we coordinated this with the architect, we basically had a large portion of our steel, especially on all the perimeter framing, defined as just these 3D shots of what the model had. And this is an example of an area where there was a lot happening. So we would kind of show like a step-by-step segment of the model to clearly show where each piece of steel was supposed to go. And within there, if there was any small pieces of steel that may have been missed, we made sure that we cut sections, so on and so forth. And then we had some of the guys in our office who were proficient with AutoCAD. They made a few blow-ups here, and it ended up turning out that we had maybe one sheet of the AutoCAD drawings, and it applied to the whole kind of surrounding cladding steel. So the next problem that we were faced with was how do we tell all of the subs and the steel fabricator how long each piece of steel is? So this is where the coordination with the architect was a huge part. What we did was the architect took the Revit model and they took every panel from the model itself, and they defined a 3D node for each panel. So what the steel fabricator did was they took all these panels and they actually modeled planes in their 3D fabrication model, and they had assumed, I think, a 4-inch offset from those planes for the thickness of the cladding itself. And then they framed the whole thing. And when we overlaid models, we found that everything lined up almost down to 100%. Another very useful aspect from a structural perspective was as we modeled the whole thing, this software has kind of a secondary system attached to it, and it's these red lines that you can see there, and they're associated with any member that you model in, and it's basically a analysis stick, I guess you could call it. And using the API that this software had, we actually modeled the whole thing, and we were able to export the whole structural model into a software called SAP, and it's basically a structural analysis software there. And for us, that was one huge thing, because to remodel this whole thing in SAP would have taken a lot of time, a lot of work. And another benefit was that we were sure that whatever our model was showing, that our analysis model was showing the exact same thing. Another useful benefit with this project was after this project was actually tendered out, we had known that there were going to be stairs added and a whole addition to the mezzanine area. So what we wanted to do was we wanted to envision or provide some sort of solution where it would minimize any impact on the existing steel there. So with the model, we made sure that any framing that had to fit in around the existing steel could kind of squeeze in between all that framing there. And that meant that whatever the steel fabricator had modeled at that point wouldn't have to change. They could just add on. And the same thing here. So there was a walkway added to the second level there, and we just provided a solution that minimized any impact with the existing structure there. So a lot of the on-site stuff, there was a lot of helpful stuff here. When we tendered this out, we released our models. However, they were for reference only. So on the right, you can see our steel model there, and it became very useful. They said that throughout the process, they essentially had our steel model overlaid most of the time, but they were using all of our sections and details to actually check everything and make sure that it was per what our drawing showed. So they said that it saved a lot of time. Another thing that we had tried out was the software had just put out this. It was a process to review shop members, I guess you could call it. So what Benson had done was they created they phased off all the steel within the roof and the whole structure here. And what they did was, instead of sending us hard copies of all these members and piece drawings, they would send us a model here, and within the model, and with each submission that they had, as you clicked on every piece of steel, the actual shop drawing associated with it would show up there, and it was a PDF. So you could provide any markups or any comments, and you could do an automatic stamp on it, and we could actually do all the shop drawing review through the model itself instead of through hard copies. Okay, so the next case study, it's the Remai Art Gallery of Saskatchewan. It's a project we've been working on for about two years now. It started in January of last year. This is just a quick fly through to give you an idea of what it looks like there. The architects are KPMG and Smith Carter. It's about a 205,000 square foot, four-story art gallery. It's located in Saskatoon, right on the waterfront. That's the space there. For all the engineers out there, it was probably one of the more structurally complex projects that we had to work on. There were two fairly large cantilevered areas there. On the east end here, there was a 14-meter cantilevered room. To make things more complicated, we had to use a truss there that would allow for all the open windows between columns. So for anyone who likes using SAP, I created a lot of structural and engineering challenges. And then on the west side, this is a quick fly through of what the concept was. So on the left hand there, you can see a 7-meter cantilevered beam. And the architect wanted this stacked box concept. So from the tip of that cantilever, there was a 14-meter cantilevered, 7-meter high room. And on the opposite end, there was another 14-meter cantilevered part of the room. And then from the tip of that 7-meter cantilever, they added another 7-meter cantilever there. So it became a very complex challenge for us to make all this work, especially being all framed in steel. However, again, using the tools that we had, we could always make sure that whatever our analysis model was showing, we can make sure that our BIM model and our drawings were showing the exact same thing. So it was nice to sit kind of and have two screens open, have one on one end, have the SAP model and the analysis model on the opposite end have the have the structural model itself, and we could go through it and kind of and make sure that things work, that things line up, things were always scaled right. And this is just a few shots of some of the analysis models and the actual structural model. And then when you combine all that, it was just a huge mess, a mess of steel. There was a lot of consideration had to be given to make sure that there wasn't too much movement in the rooms. Walking loads had to be analyzed carefully to make sure that the structure didn't vibrate. Another useful tool, and this was again learned from the previous project, we started to develop a lot of the structural. Instead of using the software for steel alone, a lot of the concrete was modeled in there. So we made sure that things like the rebar that you see there in red was shown correctly within our concrete, and any of the steel that was framing in there, we made sure that there wasn't any problems. The project was 100% done through all the coordination was done through the 3D models. So here's our model overlaid with what the mechanical had and with what the architect had. So we actually took it to the next level here, and I heard someone from TMP saying that one huge problem is that oftentimes what you see in a BIM model is not what you see on site. So with this project, we really tried to model in as much as we could in terms of most pieces of steel, things that you might see on site. So, and we made sure that whatever our model was showing, that again, we weren't taking any information from our model and transferring it to AutoCAD. We were just taking all of the snapshots directly from the model. And this is just another example here. So with this project, we had one issue because the ceilings were very high. So in some areas, the ceilings were maybe an inch or two below the bottom of our steel. So a majority or a lot of the mechanical work actually had to penetrate through all of our steel. So we took as much time as we had to try to make sure that every mechanical shaft was accounted for, and if we had to penetrate in any steel, it was all modeled in, and we tried to model all the openings too. So if it ever came up, and we overlaid models, we knew that shaft had been taken care of, and that was it. So this is just a quick fly through of all three models. Our structural is sort of shown in red. The mechanical is shown in purple, and just kind of gives you an idea of some of the coordination that we had to go through. This wasn't done. This model was done a while back, so it's not 100% coordinated, but it gives you an idea of how much time we invested into properly showing in any secondary steel and any openings, and making sure that all of the stuff fit. So back here, this is the main heart of where all the mechanical was. So basically we had to coordinate snaking everything out from that main area there. So having worked on these two projects and sort of going through the BIM process, we're starting to see and starting to think how can our office kind of take BIM and to the next level, and what are the next steps. So we found that again when we had provided our BIM steel model to the steel fabricator, that it ended up being very close. So we're starting to look at ways as to, instead of just providing, say, steel framing drawings, is there a way that we can provide maybe a set of drawings which is half the size but embed most of the information in the actual steel model itself? I think we're still a ways away, but again, I think it all really depends on the consultants being sure that everything is coordinated well. And I'm not sure if this is a good thing or a bad thing, but I think using BIM and 3D, it kind of gives an architects an opportunity to make things as complex as they want. So as long as they can make a massing of it, I think they always feel comfortable that there is some structural system out there that'll be able to make it work. So that was kind of quick, but I hope you guys picked up some new stuff. If there's any questions.
I just had a question. Like you obviously did a lot of work in Tekla, working with Benson. I know they go out to third parties that develop their Tekla shop drawings for them. Did you guys explore providing the Tekla model directly to them, and then they would do the connections, or what kind of connectivity did you have there?
Yeah, so I guess that's one aspect of it that we're looking at it now. The problem that you encounter with that is you basically take it upon yourself that you say that your model is 100% right. So if the architect were to change anything, then it kind of falls upon you, because if they're using your model for the shop drawings, then if a beam is say three inches off and a slab edge falls where it's not supposed to fall, then they always say, well, you were the one that provided the actual shop drawing model itself. The way that we've taken care of that for these two projects specifically is that we've provided the model. If they have questions about certain areas or they're not sure what our drawings are showing, they can refer to the model itself. But they always are held responsible for actually finding lengths of steel members and that kind of stuff, either through our drawings or through the architects.
So the drawings governed,
Exactly.
But you did supply the models for reference.
Right.
And then they basically took your Tekla model and they inherited the work and then probably went through it and corrected it or kept it
Pretty
current
much.
with changes. So you did a lot of work though to take your model and extrapolate that down to 2D so that then they could go back and put it in 3D. So you mentioned that like with some of the sections that it was taken out of Tekla into AutoCAD to be cleaned up. So does that mean you're actually adjusting where the members were cut through in AutoCAD, like departing from the actual cut through the steel structure?
Right. So that was kind of one example that we had when we were first working on that project. That was the first time that we had used the software. So we found as we were cutting some of these wall sections that it didn't look right. So we just tried to take it to AutoCAD to clean things up. But again, we found we were losing too much information, like you're saying. And anytime the section itself had to change, we'd have to re-export it and actually clean the thing up. So we scrapped that whole thing, and we just kept everything in one software. So if we did all the steel modeling in one software, we cut the sections there, we kept it all there. And at this point, we don't export anything out from one software to AutoCAD.
Yeah, you would run into all sorts of complexities there, because if you're moving, when you export a section directly, you have a record of where you took that section through the model, right?
Right.
And you go to AutoCAD and adjust it, it ceases to be a reference to that section. Right? It's like a theoretical section now.
Yeah, and again, I mean, for that specific project, we weren't too worried about, for example, like you talk about working points, so on and so forth. We weren't providing any of that stuff. The architect took that upon himself, and they provided again all those 3D nodes. So, to argue that fact, I mean, they were referring to our drawings. We were just showing 3D snapshots of what a steel frame.
So the control points were supplied by the architect based on the exterior skin.
Pretty much.
And then the steel geometry had to be worked backwards from the skin. Okay, cool. Thanks.
Okay. Anybody else?
Two questions. The
Sure.
first one is about the fabrication model done by Benson.
Okay.
Did you reuse it for coordination purpose afterward? Did you pick up the model they sent you?
Personally, we didn't use it, no. After we had tendered out our project, there was no purpose of us having it. For that specific project, PCL was in charge of a lot of the on-site coordination. So I know that they had a steel model, and I apologize, I don't know if it was ours or the one that the fabricator made. But again, when we overlaid our model with the fabricators, we found that it was very, very close. So PCL did always have a BIM model on site, and they did refer and coordinate all the shafts, all the ducts, all the steel with a steel model.
Okay. And the other question, you insist at the beginning of your presentation about if you model 3D properly, then you can have any 2D drawing showing anything you want. So why weren't you at HEAS giving the model not as a reference only, but as a contract document? If you model it into Tekla directly, and the drawings were made through Tekla as well. So,
Well, again, I mean, it raises all these concerns as to who's responsible for what. So, I mean, we develop our BIM models as far as the consultant team does. So if we were to say tender out and it's coordinated 75%, and we know that there's small things like slab edges or some things like that where a steel beam might have to shift, right? Then that whole onus falls on us, right? So if we were to provide a steel model and say this is the steel shop drawing model, and then when they're looking at the architect's model, again, like the famous thing is, we found because of the slab edges moving a lot, steel beams might have to shift an inch or two. So I think if we capture, most of what we're trying to show, and we did capture a lot of things I think we would have missed if the whole thing was just done in CAD. It still
but I mean,
helps.
your 2D drawings doesn't show those changes anyway, because they're not in the model. How can you show that in the 2D drawings? So it wasn't there at all. So, I mean, it's normal contract coordination, whether you have it in 2D or in 3D to start with.
Fair. I mean, yeah, it's fair to say that maybe most of the primary steel will be 100% coordinated.
And that
But
can
we
be a
found-
guarantee. We guarantee structural steel, and all the miscellaneous stuff for the docking and everything is not coordinated yet, and it's the fabricator's job to do it. That can be something to think about.
Right, but I mean, again, to actually tender out a steel model, I think we're still a ways from actually having that, right? Because again, if you're putting the whole onus on yourself that you're 100% certain that at that point all the consultants have provided all the information that you need for 100% coordinated the model, I doubt that anyone out there, whether it's mechanical or the architects, would give their BIM model out and say, well, we're not just tender out this, right? Because you still know that there might be a wall section or something that might change, or might be used around the structure. You don't necessarily have to model every piece of steel. So for us as well, there's a lot of secondary steel. If we know it's not going to interact with any of the shafts or any of the mechanical stuff, we might show it on plan, but we might not necessarily put it into our model.
Got it. Thank you.
Okay.
Question on coordination
Sure.
between the multiple disciplines. When you would export out of Tekla, you would bring that into Revit for your concrete as IFC
Yes.
and back and forth?
Pretty much. Yeah.
So you were sending IFC files out to, let's say, the mechanical and architect for them to reference into Revit?
No, that
To
was
do coordination?
Yeah, that
Or
was.
did you use like
sorry.
a Navisworks program and everybody just had to use Navisworks to see if there was a clash?
No, the one advantage of the IFC, and that was one obstacle that we had as well. When we first started the first project, because we were using two softwares, we would send the architect an IFC file, and they would be importing the IFC file. But it became a hassle, so we just realized that all we had to do from our perspective was we always had to send two separate files. We would send one concrete file, and that was a Revit file. And what we would do is we would export internally in an IFC file. We'd import it ourselves into the Revit software, and then we would just save a separate Revit steel model. So when we were to coordinate and post models, it would be two separate Revit models, but it was always Revit models.
Did you have issues with exporting to IFC from Tekla, that it might not be exactly what was drawn in Tekla?
We did a lot of work into making sure that things worked well. There's a lot of settings within the software, and we took a lot of time to make sure what we exported out was right. And I find that, again, all the lessons learned from the first project, when we got to the second project now, we've always exported the entire project as an IFC file, and it exports everything fine. So we've taken it, again, as far as modeling all the openings through our beams. We've been modeling steel plates through some of the beams, all this kind of stuff. And whenever we have a coordination meaning whether it's through the 3D model that I provide, or we're looking at the screen that the architect has of our RFC file, things always line up well.
Did you create sheets in Tekla for actually hard copies?
We did for the first project. After, again, trying many ways to just make it as efficient as possible for us, we found that I think the easiest way, or one way that we might move forward, is we'll actually be creating sheets within that software, but then we'll be exporting that out to AutoCAD. And once it's out in AutoCAD, those CAD files will never actually be opened up or changed. We just find that putting things like borders, so on and so forth, within AutoCAD is a lot more straightforward. And if we want to export anything in terms of AutoCAD from a mechanical model or from an architect's model, it's easier to overlay CAD files exported from the Tekla software, and exported from the Revit software, and compare things there. So again, we still don't have a 100% concrete way. There's been a couple of projects where we've done it one way, another project we've done it a separate way. But I think we're starting to zero in on, if we do choose at this point to do all of our modeling for steel and for concrete in the one software, I think we'll be developing all of our sheets there, and then we'll be exporting that to CAD. And then obviously within your office, you always have your CAD standards set, and we will be printing everything from that.
Okay, thanks.
Great, thank you.